Hi, students. Now let's look at your assignment questions. For problem number 1, we have a solid formed by revolving the area enclosed by y equals 2 square root of x, the x-axis, and x equals 15. And this area is revolved around the x-axis, and we want to find the volume and surface area of this solid. Okay, before we do anything, we should try to graph this area. So y equals 2 square root of x should look something like this, and the x-axis and x equals 15. So we have something like this. So when it is revolved around the x-axis, it is shaped something like this. Okay, now we want to find the volume of this surface area. So now here, this is x, this is y, and 0, and this is 15. So we can use our formula here because our solid of revolution is formed by revolving this area. We can write it as integration from 0 to 15 and pi 2 square root of x squared times dx. Okay, the reason why we can write this is because we know that if we cut a very thin slice of the volume, then the thin slice would have a width of dx, and the radius here would be 2 square root of x. So we can write the volume of the thin slice as pi r squared times dx, where r is now 2 square root of x. And then we want to add these slices together to get the volume of the solid. Okay, so we integrate it from 0 to 15 because now the x coordinate is ranging from 0 to 15. Okay, so now we can proceed on to evaluate this definite integral. So here we have 4 pi x dx. Okay, so you factor the 4 pi out, and then you have x dx. So you have 4 pi 1/2 x squared. This is just using the power rule. And then 15, 0. Okay, so now you have 4 pi times 225 over 2 minus 0 over 2. So this is equal to 450 pi. Okay, this is for the volume of this solid, and now we want the surface area of the solid. And we talked about this, like the surface area can be derived using another formula, where here we're slicing it and adding up the volume, and for the surface area we're slicing it and adding up the surface area. So now the surface area can be written as 2 pi r times the length of this very small segment. Okay, and we know that this very small segment can be written as 1 plus dy dx squared dx. Okay, where y is 2 square root of x. So because y is 2 square root of x, dy dx should just be square root of x taken the reciprocal. Okay, so now you can evaluate this integral by writing this as this is x over x plus 1 dx, which is equal to 0 to 15. 4 pi, you can cancel the square root of x out, and here you have square root of x plus 1 dx. Okay, so now we can use substitution, or like you can use the eyeball method to see that this should be equal to x plus 1 to the 3 over 2, and then times 2 over 3. Okay, 15 and 0. Okay, so this is equal to 8 pi over 3 times 16 to the 3 over 2th power minus 1 to the 3 over 2th power. Okay, so because this is the 3 over 2th power, you should square root it and then take the cube. So you have, this is 4 to the 3rd minus 1 to the 3rd. Okay, so this is equal to 8 over 3 pi times, this is 64, so this is 63. Okay, so this is equal to, cancel this out and get 21, and eventually you get 168 pi. Okay, so basically, after you have graphed this function and this area on the Cartesian plane and find that like it is a very nice shape, you can just use the formula we taught in the class and then evaluate the definite integral. Okay, so now let's go to problem 2. So in problem 2, we said that in class we derived the volume of a ball of a radius of r as 4 over 3 pi r cubed. And we derived this using the method of disk. So previously in class, we constructed this curve. We say that this curve should have equation y equals square root of r squared minus x squared. And this is derived from the equation of a circle, and then we take the positive root of y and we get this equation. And we found that if you revolve this curve around the x-axis, it would form a ball. And then we use the method of disks to find this volume of the ball. And now in problem 2, we're trying to use the method of shells to find the same volume. Okay, so for method of shells, let's just first complete the ball here. So the ball is looking something like this. Okay, so if we use the method of shells, basically we're trying to use like thin cylinders and then cut, use these thin cylinders to cut the ball into like very little slices and then add up these cylinders. Okay, so if we can put a cylinder here and then cut. Okay, sorry, I should draw it like this. Okay, okay. You see that this is a cylinder here, and like we let the width of the cylinder be very small, which is dx. Okay, so basically if you take it out, then it would look something like this. Okay, so this is a very thin cylinder. Okay, and the width here is dx. Okay, now the width is dx. And for this cylinder, we have the length x. So if you draw it here, you have this is x. Okay, so now we have to find the volume of this cylinder, right? So because the x coordinate here is x, so if you see here, the x coordinate here is x. So if we want to find the height of this cylinder, we just need to double like this length, right? Which I marked in like double primes. Okay, so what is the length of this? So length of this should be square root of r squared minus x squared, right? Because the length of this this segment should be the y coordinate of this point I marked here. Okay, and y coordinate of this point should be square root of r squared minus x squared, because we know that the x coordinate of this point right here is x. Okay, So half the length, or like half the height of the cylinder, should be square root of r squared minus x squared. So the height, the total height of this cylinder should be 2 times r squared minus x squared. Okay, so the volume of this very thin cylinder can be written as 2 times r squared minus x squared times 2 pi x, okay, and times dx, okay. We talked about this, like if you want to find the volume of this very thin cylinder, you can imagine that you have a scissors here and you cut it along this line, right? So if you cut it, it will become a very thin sheet, and the width of this sheet should be dx, and the height of this sheet should be the original height, which is 2 times r squared minus x squared. Okay, and here the length here should be the perimeter of this the base. So because the base have radius x, so the perimeter should be 2 pi x. Okay, so the total volume of this thin sheet should be 2 pi x times 2 times square root of r squared minus x squared times dx. Okay, so now we have this. We want to integrate on this term because we want to add up all the volumes of the cylinders. Here we integrate from 0 to r, okay? We're not integrating from negative r to r because we know that when x is 0, then you have a very thin, very thin cylinder. And then when x goes from 0 to r, these cylinders add up to the whole ball. So you do not need to let x be negative, because once you have added up from x from to 0 to r, then you have finished adding up the volume of the ball. So we integrate from 0 to r. Okay, so now we have this definite integral. We can factor out the 4 pi here, and then get this is x times square root of r squared minus x squared dx. Now we can use u substitution, where u is equal to r squared minus x squared. And because u is equal to r squared minus x squared, so du is equal to negative 2x dx. Okay? And because we're doing a definite integral, we also have to know how we need to transform the upper and lower limits of the integration. So here, when x is equal to r, then u is equal to r squared minus r squared, so u is equal to 0. And when x is equal to 0, which is the lower integration limit, we have u equals r squared minus 0, so u is equal to r squared. Okay? So now let's prep our definite integral so that we can do u substitution. So we need negative 2x dx. So here we divide by negative 2. Sorry. And then here we have square root of r squared minus x squared, and you have negative 2x dx. Okay, so now we have prepared our integrand to do u substitution. So after u substitution, the upper and lower integration limits should change into 0 and r squared. And here you have square root of u and du. Okay? So this is equal to negative 2 pi integrate r squared to 0. This is u to the 1/2 power. Remember that square root is just 1/2 power. And then you can use the power rule to get this is equal to, the antiderivative should be 2/3 times u to the 3/2. And then here you have 0 and r squared. Okay? Okay, so here you can reverse the upper and lower integration limit, and this is equal to 2 pi times 2/3 u to the 3/2 r0. Okay? So for the lower limit here, if you plug in 0 into u, you get 0. So you only need to plug in r into u, so you get r to the 3, sorry, r squared to the 3 over 2. Okay, so r squared to 3 over 2, you can multiply the exponent to get r cubed. And for the constant in front of it, you get 4 over 3 pi, which is exactly the same volume we got when we're using the method of disks. Okay, now let's look at problem 3. So in problem 3, a solid is formed by revolving the area enclosed by y equals 1 over x, y equals 2, the x-axis, the y-axis, and x equals 2. And this area is revolved around the y-axis. Okay, so let's first look at the shape of this area and see like what's the shape of this solid of revolution. So if we plot y equals 1 over x, you get something like this. So if this is 1, this is 2, this is 1, this is 2, then here you have 1. And when it should go through 1 1, because like if you plug in 1 into x, then you get y equals 1. And also here, when x is equal to 2, y is equal to a half. And when x is equal to a half, y is equal to 2. So you have a curve shaped somewhat like this, okay? And here we also have y equals 2. So y equals 2 should be this line, okay, which is parallel to the x-axis. And now we have x-axis, y-axis, and x equals 2, okay? So you can see that the area enclosed by these 5 curves should be this, okay? So if you revolve it around the y-axis, remember we're revolving around the y-axis, you would get something like this, okay? Okay. So this is the other half here. And then you revolve it around the y-axis, you will get something like this. Okay? Okay. So we want to know the volume of this solid, okay? So for the volume of this solid, you can see that you cannot evaluate it within one integral, okay? Because this solid is like, the area that is forming this solid is very complex. So you have basically you have a lot of different ways to cut this solid into different like subsolids, and then you can evaluate the volume of these subsolids like one by one, and then add them together. Okay. So here, what I'm trying to do is to cut this solid into 2 parts, which is shaped like this. So let's first look at here. If you cut this solid around here, okay? Okay, so you can see that like this solid can be cut into 2 pieces like this, okay? So this is the upper part and this is the lower part, okay? So now let's look at the dimensions of these solids. So for the first solid, it looks like a cylinder. It is actually a cylinder. So what is the height of this solid? The height of this solid is actually the y coordinate of this point, right? So the y coordinate of this point, here you can see that because its x coordinate is 2, because this is 2. So this point is 2 1/2. So here the height is 1/2, okay? And because it's a cylinder, we also need to know the radius of its base. So its base, the radius is this length, right? So this length is just 2. Okay, so the volume of this cylinder is actually easy. You can just write pi times r squared times 1/2, which is equal to 2 pi. Okay. Then let's turn to the volcano-shaped solid on the above. Okay. So here you can see that you can use the method of disks to find the volume of this solid. So for this solid, maybe I should. Okay. Okay, so for this solid, we can cut it like this, okay? Where here you have a y coordinate of y, okay? So basically we're trying to cut this solid into many layers of disks and then add these disks up so that we can find its volume, okay? So for this very thin disk, first, because we're cutting this solid along the y-axis, so the height here should be dy, right? And then here you have a cylinder-like disk. So we want to find the radius of this disk. And the radius of this disk, to find it, you have to go back to the Cartesian plane where you see that the radius of this disk is actually the x-coordinate of this point, right? And the x-coordinate of this point can be found by using the y-coordinate of this point, because the y-coordinate of this point is y, and this curve is actually y equals 1 over x. Okay, this curve is y equals 1 over x. So if the y-coordinate is y, then the x-coordinate should be 1 over y, right? So here the radius is 1 over y. So we know that the volume of this disk should be 1 over y squared times pi. This is the area of the base, and then we time it by dy. Eventually we want to integrate this thin disk, right? So we have to find the range of the y-coordinate. And the range of y-coordinate, here the y-coordinate is 2, and here the y-coordinate is 1/2, okay? You can look up here. Like here, the y-coordinate here is 2, okay? And here we just derived that the y-coordinate of the base should be 1 over 2, okay? So integrate from 1 over 2 to 2. So here you take the pi out, and then you get 1 over 2, and this is y to the negative 2 power. Okay, so this is equal to pi, and this is y to the negative 1, negative 2. Okay, so this is equal to pi, and then this is negative 1/2 minus negative 2. Okay, because for the lower integration limit, you have negative 1/2 to the negative 1 power, which is the reciprocal. So the reciprocal of 1/2 is 2, so you get negative 2. So eventually you get 2 minus 1/2, which is 3 over 2 pi. Okay, so this is 3 over 2 pi. So you can add these up and then get 3 over 2 pi plus 2 pi, which is equal to 7 over 2 pi. Okay, so this is for problem 3. So you notice that for this problem, you have to cut the solid into different pieces so that you can get its volume. And another way to cut this solid is actually you can try to cut it this way, which is here you cut it along the x-axis and you get a very long cylinder, and the remaining solid here is shaped like this with a hollow like inner core. Okay, so here you cut here so that this part is cut it out, and then for the remainder you have a still a volcano shaped thing, but like it has a hollow core. Okay, so for this shape you can use the method of cylinders to try to find its volume, and for this one this is just a cylinder, so you can find its radius of the base and its height, which is 2, and then you can add these together, and you can still get 7/2 pi. Okay, so for the last problem, we have the Gabriel's horn, which is constructed by revolving the curve of y equals 1/x, where x is greater or equal to 1, around the x-axis. Okay, so if we plot it on a Cartesian plane, you can see that this is 1 and 1. So if we draw the whole y equals x, 1/x, it should look like this. But now we're not looking at where x is smaller than 1. So if we revolve this curve along the x-axis, we would get something like this. Okay, so this is called Gabriel's horn because it is shaped like a horn. Okay, and we want to find the volume of the solid of this pi. Okay, the volume, find the volume of this solid of revolution, which is pi. So the volume of this solid of revolution is quite easy because you can just use the formula we taught for solid of revolution. So here you can integrate from 1 to infinity. So here we're integrating from 1 to infinity because the Gabriel's form is actually have an infinite length here. So it goes to the right on and on until infinity. So the x-axis is starting from 1, but it is ending at infinity. You can think of like this is actually a limit, but like the end of this horn is actually infinitely far. Okay, so for the integrand, you have pi r squared, or like a pi f of x squared times dx, right? So you have pi f of x squared and then times dx. Okay, so if you evaluate this, you get this is equal to pi times integrate 1 to infinity. This is actually -2, right? So using the power rule, you get this is x to the -1 and take a negative. Okay. Okay, and we talked about this, that if you have an improper integral and you have a infinity in your upper limit or lower limit, actually you want to take the limits towards infinity. Okay, so this is equal to pi times limit x goes to infinity negative like 1/x, which is x to the -1, minus, when like for the lower limit you can just plug 1 in, so this is -1. Okay, so this is equal to pi 1 plus limit x goes to infinity negative 1/x. Okay, so when x goes to positive infinity, then 1/x would be a very small positive number, so this limit goes to 0. So this is equal to pi, which is our result. Okay, so that's it for our assignment. Okay, now let's pick up from what we have left off last week. So last week we started talking about improper integrals. So improper integrals are some kind of definite integrals that is not like allowed by our previous definitions, but we want to expand our definitions of definite integrals so that we can use the same technique to evaluate something we're interested in, but like do not fit our previous definition. So for example, maybe we want to find something like this. So like this integral, actually, if you plot it like e to the negative x, okay, so e to the negative x should be looking something like this. So if we're interested in this area under curve, like up to infinity, then like intuitively we would write something like this, like for our definite integral. But like for our previous, like a more restricted definition of definite integrals, you cannot put an infinity or negative infinity on your upper or lower integration limit. So we expanded our definitions of definite integrals into improper integrals by letting this be equal to limit b goes to infinity 0 to b e to x dx. Okay, so this is the formal definition of this this type of improper integrals, which you have infinity or negative infinity in your upper or lower integration limit. But eventually we will see that like actually you can omit the limit signs by just treating infinity just as a number, although it is not a number, but you can treat it as a quantity. And then when you're trying to evaluate your antiderivative at infinity, you can just use limits. So for example, for this one, you can write this is equal to negative e to the negative x infinity 0, right? So now we're looking infinity as if it is a number, but it is not. Okay, so for the upper limit, you can just evaluate limit x goes to infinity negative e to the negative x. So this is the upper limit, which we want, like you can think of like we want to evaluate negative e to the negative x at infinity. Okay, and for the second term, you can just write negative e to the negative 0. Okay, so here, because when x goes to infinity, then like negative x is a very negative number, so the whole exponent would be 0, go to 0. So this is equal to 0 minus negative 1, which is equal to 1. Okay. Okay, these are improper integrals, and now let's pick up from where we left off, which is subproblem C in example 7.11. Okay, so example 7.11. So for problem C, we want to evaluate this 0 to infinity x e to the negative x dx. Okay, so notice that we now have a form of integral where we need to use integration by parts. Okay, so using integration by parts, we have two choices, right? We can use u equals x and v dv dx is equal to e to the negative x, or u is equal to e to the negative x and v is equal to, dv dx is equal to x. Okay, but you can see that because eventually, like in integration by parts, we want to differentiate u, right? So for this choice, if you differentiate u, it is not simplifying the function. Like if you differentiate e to the negative x, you get negative e to the negative x, which is not simplifying. And here, dv dx, you want to integrate it, which goes to some multiple of x squared. So you're actually making the things worse if you use this like choice. So we do not use this choice. So we let u equals x and dv dx is equal to e to the negative x. So under this choice, we have du dx, it should be equal to 1. And v, we choose one of its antiderivatives, so we choose negative e to the negative x. Okay? So we can write this improper integral using integration by parts. So the first term is uv, so this is x, which is u is equal to x, and v is equal to negative e to the negative x. Okay, and then minus the integral of 0 to infinity And here we have du dx times v, right? So du dx is 1, and v is negative e to the negative x dx, okay? But here, remember that like we are doing an indefinite integral, so here you also have infinity and 0, okay? You have to evaluate it at, like we say, at infinity and 0, and then like subtract them, okay? But here, by talking about evaluating the value at infinity, what we really mean is taking the limit when x goes to infinity, okay? Okay, so this is equal to negative x e to the negative x, infinity is 0. And you can, here you have, this is negative e to the negative x dx, okay? So this is equal to negative x e to the negative x, infinity is 0. And if you anti-differentiate this, you can see that its antiderivative should be e to, one of its antiderivative should be e to the negative x, because e to the negative x dx is just negative e to the negative x, right? So here you have minus e to the negative x, and then you evaluate at infinity and 0. Okay, so for the first term should be limit x goes to infinity, negative x e to the negative x, right? This is like what we say that we evaluate negative x times e to the negative x at infinity, okay? And for the next term, we have negative 0 times e to the 0. So like you get 0, so this is 0. Okay? Okay, now let's look at the second term. For the upper limit of integration, you get e to the negative infinity, right? So in principle, we still have to write out the like limit, but like we can think of it, because x is going to infinity, negative x is going to negative infinity, and e to the negative infinity, like when you draw the curve like this is e to x. So e to the negative infinity should tend to 0, okay? So here, the upper limit of integration, we get 0. And for lower limit integration, you get e to the negative x, which is e to the 0. So this is equal to 1. Okay? Okay, now for the first term, if you like remember, like previously we talked about limits, you may know that like this limit should go to 0, okay? But if you do not remember anything about this, you can still like evaluate it from scratch, okay? So here you have limit negative x times e to the negative x. So the first thing, like for limits, the first thing we do is the plug-in method, right? So if we don't do plug-in method, you get negative, then x goes to infinity. Then e to the negative x, we said that like when x goes to infinity, e to the negative x should go to 0, right? We used it in this term. Okay, so this should be 0. So you get what? You get an indeterminate form. We said that we had a lot of indeterminate form, right? 0 times infinity, infinity over infinity, 0 over 0. I can write it out like indeterminate forms. We said that you may have something like infinity minus infinity, 0 times infinity, infinity over infinity, 0 over 0, and there are something like 1 to the 0, infinity, something like these, okay? Okay, so here we have a infinity times 0. So one thing we can do is to use the L'Hopital's rule, okay? Like before, we can use L'Hopital's rule because we know that L'Hopital's rule only applies when you have infinity over infinity or 0 over 0. So you can rewrite this limit, okay? Rewrite this limit as here, the denominator, we have negative x. So we want to move e to the negative x to the denominator. So we just cross out the negative sign, so you get something like this, okay? Okay, so here, minus 0, we just omit it. And here, for the second term, you get the minus -1, so this is +1. Okay. Okay, now we're prepped for our L'Hopital's rule because the numerator, when x goes to infinity, goes to -infinity, right? And the denominator, e to the x, when x goes to infinity, it goes to infinity. So you have a -infinity over infinity, which fits the requirement for the usage of L'Hopital's rule. So you can let this is equal to x goes to infinity, and -x, you take the derivative, and e to the x, you take the derivative. This is what L'Hopital's rule say, right? So L'Hopital's rule says that if you use the plug-in method on a limit of a fraction, and you get infinity over infinity or 0 over 0, then you can take the derivative of both the numerator and the denominator, and then evaluate the new fraction, like using the same limit, okay? So here we get limit x goes to infinity. For -x, if you differentiate it with respect to x, you get -1. And e to the x is just e to the x, okay? Okay, now when you plug in x goes to infinity into this fraction, the numerator is just -1, right? And for the denominator, you get e to the infinity, so the denominator will become a very large positive number. So -1 over a very large positive number would approach 0 from the negative side, okay? So this is equal to 0 plus 1, which is 1, okay? Okay, so you can see that like in improper integrals, because you have infinities, like one type of improper integral, you have an infinity or negative infinity at your limits of integration. So sometimes, like after you find the antiderivatives, you have to recall your knowledge on like how to evaluate limits to get your value of these improper integrals. Okay, so now let's move on to the next subproblem, which is D. Okay, so for D, we want to evaluate the integral from -infinity to 1, square root of 3 minus x dx. Okay, okay, so now like the most intuitive way to tackle this improper integral or like definite integral is that like here we need u substitution, right? Because we do not know how to integrate like square root of 3 minus x, but we know how to integrate square root of u, which we can just use the power rule. So we can try u substitution. So if we let u equals 3 over x, 3 minus x, then du should be negative dx, because you want to differentiate 3 minus x by x, which leads to -1, okay? Okay, but remember that this is like some kind of a definite integral, so after you do u substitution, you should also transform the limits of integration, okay? So we can see that when when x equals 1, then u is equal to 3 minus 1, right? Because u is equal to 3 minus x, so u is equal to 2. And for the lower limits of integration, this is a little bit tricky to write, but like you can think of like when x goes to -infinity, okay, then u, what will u go? Because x goes to -infinity, and u is equal to 3 minus x. So u will shoot up to infinity, right? Because u is 3 minus x, and x is going negative, more and more negative with a very large magnitude. So 3 minus a very negative number should be a very positive number. So u goes to infinity, okay? Okay, so remember that after we do the u substitution, we also have to change the limit of integration. And sometimes this limit of integration may be like positive or negative infinity. Okay, so here we have this is equal to the integration of 1 negative infinity and 3 minus x. So before we do u substitution, we have to prep it, like we prep our differential. So because we have a negative sign here, so we have a negative sign here. Or like, if you like, you can write it as something like this, because we know that we previously we argued that like if you change the upper and lower limit, like you exchange the upper and lower limit of the integral, it is equivalent to adding a negative sign, like a, yeah. So here we can start the u substitution. So here this is square root of u, and this is du. And for the limit of integration, you can see that for negative infinity, we say that when x goes to negative infinity, u is going to infinity. So here you write infinity, okay? And when x is equal to 1, u is equal to 2, so you write 2 here, okay? So now we can just proceed on with our usual like anti-differentiation techniques. So this is equal to 1 to infinity. And square root of u, you must be very familiar with this. Square root of u is just u to the 1/2 power, okay? So u to the 1/2 power, you can use the power rule and get the antiderivative of u to the 1/2 power. Should be u to the 3/2 power times 2/3, okay? And here you have infinity and 2. Okay. So now we have to evaluate this function at infinity, or like its limit toward infinity, and 2. So this is equal to limit u goes to infinity 2/3 u to the 3/2, okay? Minus 2/3 2 to the 3/2. That's right. Okay. Okay, now it is clear that for this term, when u goes to infinity, u to the 3/2 power should also go to infinity. So the whole thing goes to infinity. So it does not matter like what the constant here is, because the first term goes to infinity. So this limit is going to infinity, okay? So you can write that these improper integrals do not exist, diverges, or you can write like it is equal to infinity, because like the limit goes to infinity, okay? Okay, so now let's move on to E, subproblem E. So for subproblem E, we want to find the integral of from negative infinity to -1, e to the 1/x, and this is x squared dx, okay? Okay, so for this integrand, like to do anti-differentiation, what we want to do here is to use u substitution, right, and see if it works, okay? So if we do u substitution, there are some choices we can make. For example, we can guess that like we let u be the denominator, so u equals x squared, but you can try it and you can see that it does not work, because you cannot deal with e to the 1/x power like with this substitution. So another way to tackle it is to let u equals 1/x, okay? So when u equals 1/x, then du should be equal to -1/x squared dx, because you have to differentiate 1/x, right? And you can see that 1/x squared is actually here, okay? So this actually works. So we're trying to use this u substitution to get our result. And don't forget that here we're doing a like improper integral, like with definite integral. So here we have to know that when x is -1 or x goes to negative infinity, what does u go, okay? So if x is equal to -1, then u is equal to 1/-1, because u is equal to 1/x, right? So u is still -1. And when x goes to negative infinity, then you can see that u should go to where? Because x is going to negative infinity, so u is 1 over a very negative number, right? a very large negative number. And so u is actually going to 0 from the left hand side, right? So u is equal to 0. Okay, so here we can proceed on with our prepping of u substitution. So this is equal to integration negative infinity to negative 1. Here we want negative 1 over x squared dx, right? So you see that we're adding a negative sign within the integral, so we have to have a negative sign here. Or like you can exchange the limits of integration and get something like this. Okay, so now we can do u substitution. So here u is 1 over x, so this is e to the u, and for the differential we have du. And don't forget that you have to change the limits of integration. Okay, so when x is negative 1, u is negative 1. And when x goes to negative infinity, u actually goes to 0. So you write 0 here. So here, like before u substitution, it is a improper integral, but after u substitution, it becomes just a regular definite integral. Okay, so here you can integrate e to the u, which is e to the u. So e to the u, you evaluate from 0 and negative 1. Okay, so this is equal to e to the 0 minus e to the negative 1, which is 1 minus e to the negative 1. Or you can write it as 1 minus 1 over e. Okay, so this is subproblem E, which involves E. Okay, now let's look at the last subproblem for this example. Okay, so for the last subproblem, we want to integrate from negative infinity to infinity x to the third, x to the fourth plus 1 squared dx. Okay. Okay, so for this integrand, maybe you can try, like at first you maybe think of like, this is a rational function, right? Maybe I can use some kind of like a partial fraction decomposition, but that is too cumbersome. Actually, if you see, like you try u substitution first, then like if u is equal to x to the fourth minus 1, which is very natural choice for u, right? Because it is in the denominator. Then you can see that du is actually equal to 4x cubed dx. And you can see that x cubed is actually here. Okay? So you can just use u substitution to tackle this integral. Okay? And like we have gone through this like many times. So because this is an improper integral which stems from definite integrals, so we have to know like what the limits of integration would be after we do the u substitution. So we say that when x goes to infinity, notice that here both the upper and lower limits are constituted with infinity. So when x goes to infinity, then because u is x to the fourth minus 1, so u also goes to infinity, right? And when x goes to negative infinity, surprisingly, we see that because negative infinity taken the fourth power goes to positive infinity, so u still goes to positive infinity. Okay. So now we get this is equal to integration of negative infinity to positive infinity. Here you have x to the fourth plus 1 squared, taken the reciprocal. And for the differential, we want 4x cubed dx, right? So to balance the 4, we have a 1/4 here. Okay. So now we can do u substitution, and this is infinity, because like we know that after u substitution, the upper and lower limits both are infinity. Okay. But to be rigorous and like careful, we do not say that because they are all infinity, so that like this should be equal to 0, because we have to make sure that both we have to make sure that the antiderivative, when taken the limit to infinity, it exists. Okay, we will see why this is okay. So this is du. Sorry, this is not u plus 1, because we let u equals x to the 4th plus 1. So this is u squared, okay? So this is equal to 1/4 negative 1 over u, infinity. Okay? So here, in principle, we should write this as limit x goes to infinity, negative 1 over u, minus limit x to the infinity, negative 1 over u, okay? So previously I said that like we should not just write this is equal to 0 right away, because this is actually defined as this equation, okay? And like this equation involves two limits, that is evaluating a function at infinity. So if like this function does not exist, like if this limit does not exist, then we cannot say that like this the improper integral is 0, okay? So previously we say that you can think of infinity as a number, but like actually in the back of it, it is still doing limits. And like when we do limits, you have to think of the possibility that the limit does not exist, or like it blows up to infinity or negative infinity, right? So we have to check, okay? We have to check if these two limits, although they look the same, these two limits are exist, okay? And fortunately, like these two limits both exist, because when x goes to infinity, 1 over u should go to 0. So negative 1 over u also goes to 0. So this is equal to 1/4 0 minus 0, which is 0. Okay? You may be thinking like, why is it like after we do the u substitution, then we get like the same upper and lower integration limits? This is because here, if you graph the function out, which is also shown in your handout, you can see it is shaped as something like this. Okay, so this is called an odd function. Okay, this is f of x is equal to x to the 3rd, x to the 4th plus 1 squared. Okay, and this function is called an odd function because f of x is equal to sorry, you can write it as, because f of negative x is equal to negative f of x, okay? You can see that for this function, if you plug in negative x in it, for the denominator, you get exactly the same thing, right? Because if you plug in negative x into here, then it is taken to the 4th power, and then like the negative 1 actually just vanishes. But for the numerator, the negative sign, when taken to the 3rd power, it is still negative 1, right? So you can get f of negative x is equal to negative f of x. And any function that has this property is called an odd function. And the thing about odd functions is that if you integrate it over the real line, then you can see that here you have a negative area, because this is a signed area, and here you have a positive area, okay? And because this function is actually somewhat symmetric over, like mirrorly symmetric over the x-axis, so the blue area and the red area is actually same in magnitude, but the blue area would be negative because we're using signed area, and the red area would be positive, so they would cancel. So here in this problem, we can see that the value for the improper integral is actually 0. But there is also a possibility that you have an odd function. But if you integrate it from negative infinity to positive infinity, it is not 0. This happens when either area goes to infinity. Okay, so for example, here we say that this improper integral is equal to 0 as long as the area of the blue and the red, the blue area and the red area both are finite. Okay, but if you have something like this, which is y equals x, y equals x is also a odd function, because if y equals f of x is equal to x, the f of negative x is negative x, which is negative f of x, right? So y equals x is actually a odd function. But if you try to write something like the integral of negative infinity to positive infinity x dx, then actually it does not evaluate to 0, okay? Because here for the left hand side and the right hand side, the red area and the blue area, when you're integrating to infinities, they're both infinities. So this leads back to what I have emphasized, that when you see infinity and infinity at both integration limits, you cannot just say that like this improper integral evaluates to 0, because it only evaluates to 0 if these limits exist. That means that if these areas do not go to infinity. Okay, so after you have checked that like these limits do not go to infinity, then yes, like for an odd function, this improper integral, when you integrate from negative infinity to positive infinity, should be 0. Okay. Okay, let's have a break. Okay, let's proceed on. So previously we talked about one type of improper integrals which looks something like this, right? So this type of improper integrals are improper because one or both of its limits of integration is infinity or negative infinity. So we know that like for these type of improper integrals, you just need to take the limit when you're trying to evaluate like the antiderivatives at infinity or at negative infinity. Okay, so now we're looking at another type of improper integrals which shape something like this. Okay, at first glance, like it does not seem that this integral is like nothing improper, but you can see that for this integrand 1 over the cube root of x, you can see that this function, when taken to x equals 0, it actually blows up. So if you try to graph this function between 0 and 1, you can see that it is shaped like this. Okay, so it goes to infinity when x goes to 0. And previously, when we're defining definite integrals, we actually require that the integrand is actually continuous within the lower and upper limit of integration. So for this type of integrals, like it is still an improper integral, but we can extend our definitions over definite integrals so that we can evaluate this kind of like improper integrals. Okay. Okay, so now let's look at definition 7.5, which defines how these improper integrals should be evaluated. Okay, so the first one, which is is dealing with something like this. Okay, so this would shape like something like this, right? Okay, let's plot x and y. So okay, so for this okay, for this type of integral, the discontinuity, or like we say infinite discontinuity of the integrand, actually appears at the upper limit of the integration, right? Here, the problem is here. So it is occurring at the upper limit of integration. And we say that for this kind of improper integral, where write this, and then f of x is continuous between a and b, but not including b, and it has a infinite discontinuity at x equals b. Then for this type of improper integrals, you can evaluate it by first evaluating the definite integrals from a to c, and then letting c go to b from the left side. Okay, so for example, for this graph, you can see that originally we want to integrate from -1 to 0, right? But we know that the integrand is actually going to -infinity at 0, so it has a infinite discontinuity. So the way we evaluate it is we evaluate the integral, like the definite integral from -1 to c, and then we let c approach 0 from the left side. So the limits of this quantity would be defined as our value for this integral. Okay? Okay, then we can look at another scenario, which is depicted as this one. Okay, so if the infinite discontinuity is occurring at the lower limit of integration, so now f of x is continuous between a and b, but not including a, because when x equals a, it has an infinite discontinuity. Then what we mean by integrating f of x from a to b is that first we evaluate the definite integral from c to b, then letting c go to a from the positive side. Okay, so for example, in our improper integral here, originally we want to integrate from 0 to 1, but 1 over the cube root of x is actually going to infinity, or like -infinity as x goes to 0. Okay, so we can first evaluate the definite integral from c to 1. Okay, and then we let c go to 0 from the positive side. Okay, so notice that here c is going to b from the negative side, but c is going to a from the positive side. And like this negative and positive, you can easily think of it like when you have a graph in mind. So here, like for this improper integral, because originally you want to integrate from a to b, but like you cannot reach b, so you go from a to c, and then c is approaching b from the left side, so you have a negative sign here. Okay, and for this case, you want to integrate from a to b, but you have a infinite discontinuity at a, so you integrate from c to b, and then you move c closer and closer to a from the right side, so eventually you get to a. So here you have a positive sign here. Okay, although like this definition seems a little bit complicated, but actually in practice, when the infinite discontinuity only occurs at the limits of integration, then basically you can just evaluate the integral as usual, and just remember that when you're trying to plug in the values into the antiderivatives, you have to take the limit. This is just it. Okay, so like basically you would not get like erroneous answers where you forget to like write the like a plus or b minus, something like that, like in the limit. But there is another case where you can get erroneous answers if you omit the the improper integral like caused by infinite discontinuities. This is the case when the infinite discontinuity actually occurs within the range of integration. For example, if you try to evaluate something like this. Okay, so now the graph should look something like this. Okay, so basically we actually want to evaluate these. Okay, so this is the case where you're evaluating the integral from -1 to 1, but within -1 to 1, like within it, you have a infinite discontinuity at 0 for the integrand. Okay, so for this type of integral, which we like generalize it using this definition. So like if f of x is actually continuous in a and b, but except for a point, say c. Okay, so for example here, 1 over the cube root of x is continuous between -1 and 1, but except for x equals 0, because at x equals 0, it has an infinite discontinuity. Okay, in this case, when we write the integral from a to b f of x dx, this is actually defined as from a to c plus from c to b. Okay. Okay, notice that because f of x has an infinite discontinuity at c, so here the two integrals at the right hand side are also improper integrals because like it has an infinite discontinuity at c. Okay, and the pitfall here is that because if you know the antiderivative of like small f of x is big F of x, okay, so you know that one of the antiderivative of small f of x is big F of x. Okay, so if you do this and then like evaluate its value from the right hand side at the right hand side here, then actually you should write f of x limit x goes to 0. Like for the first integral, you should write something like this, right? Because this is still an improper integral, so you have to write this improper integral as some sort of limit. So here, because you cannot directly go to c, you just go from a to x, and then like x goes to c. Sorry, this is from the negative side. Okay. Okay, this is the left-hand side. No, like for the first term. And for the second term, you should evaluate it like this is f of b minus limit x goes to c from the positive side, big F of x. Okay, so for the second integral, you're going from c to b, but you have an infinite discontinuity at c, so you go from x to b, which is like f of b minus f of x, from x to b, and then you let x approach c from the right hand side. Okay, so the right hand side is actually implying like this gigantic thing. Okay, but if you omitted the infinite discontinuity and then just willy-nilly say that, okay, because I know the antiderivative or small f of x, one of it is like a big F of x, you may just write like this is equal to f of b minus f of a. And when like f of x, like big F of x is continuous, then like everything is okay. But there are some circumstances where in the right hand side, these two do not agree, or even like they go to infinity or negative infinity, so that like the from the right hand side, you actually get a conclusion that the improper integral does not converge. But in this case, if you did not write it as two integrals added together and just use this expression, then you will not detect like this information of like they may not converge. Okay. And this may sound a little bit abstract, so like we can evaluate some of the examples in the example 7.12, and we can see that like what are the pitfalls when you ignore infinite discontinuities within the range of integration. Okay. Okay, so now let's first look at example 7.12 here. Okay, so we want to evaluate for A, we want to evaluate integral from 0 to 1 over the cube root of x. Okay. Okay, so this is the example we have talked about. Okay, so we know that 1 over the cube root of x actually has a infinite discontinuity at 0. Okay, so here, because it is occurring at the limits of integration, basically we can just treat it as a normal integral, but like to remind us that like when we're evaluating the antiderivative, we have to take the limit. We can write this as the integral of 0 plus to 1 over x squared. Okay, this is because like after like this is because that like basically we're trying to take the limits at the lower limit. Okay, so we write 0 plus because we're approaching 0 from the positive side here, and because 0 is at 0 we have a infinite discontinuity. Okay, so if we write this improper integral like this, then we can proceed on by finding the antiderivative of 1 over cube root x. Okay, so this is equal to u to the negative 1/3. Okay, and using the power rule, you get this is 2 to the 2 over 3 u to the. Okay, this is 1 and 0 plus. Okay. Okay, so like here we have 0 plus here because at this stage where we're trying to like evaluate the antiderivatives for the lower limit of integration, we have to take the limit, and this limit is approaching 0 from the right hand side. Okay, but like for this case, this actually does not matter because now our antiderivative is actually continuous at 0, so you can just plug in 0. Okay, so here you get this is equal to 3 over 2 times 1 minus 0. Okay, 3 over 2 times 0, so this is 3 over 2. Okay, okay, this one is relatively easy. So now let's look at subproblem B, where we want to integrate from 0 to 1 over x to the third dx. Okay. Okay, so now we see that this seems like it is a definite integral, but if you look closely, you can see that the integrand 1 over x to the third actually has a infinite discontinuity at 0, which is the lower limit of integration. So to remind us that like after this, when we're trying to evaluate the value of the antiderivative, we have to take limits. We can write this integral as something like this. Okay, so basically after you find the antiderivative for a lower limit, you have to take for a lower integration limit, you have to take the limit where x goes to 0 from the positive side. Okay, so now we can use the power rule to get this is equal to negative 1/2 x to negative 2. Okay. Okay, so here you can see that this is equal to For the upper limit, you can just plug it in. So this is negative 1/2 because 1 to the negative 2 like power is just 1, okay? And you have to minus limit x goes to 0 from the positive side, negative 1/2 x to negative 2. Okay? Okay, now we can see that when x goes to 0 from the positive side, okay, we can write this as something like this. Okay, when x goes to 0 from the positive side, the x squared goes to 0 from the positive side. So 2x squared also goes to 0 from the positive side. So 1 over 2x squared would go to positive infinity. Therefore, this whole expression would go to negative infinity as x goes to 0 from the positive side. So you have minus 1/2 minus negative infinity. So eventually this will blow up to infinity, okay? So for this improper integral, it actually evaluates to infinity, or like you can say that this improper integral just does not exist, okay? Okay, so now let's look at C, okay? So for C, we're trying to evaluate from 0 to infinity, square root of x, x plus 1, taking a reciprocal dx, okay? So here, it is evident that this should be an improper integral because we have an infinity at the upper limit of integration. But also note that the integrand, which is 1 over square root of x times x plus 1, also have a infinite discontinuity at 0, okay? So like the infinite discontinuity for this function is at 0 and negative 1, but because we're trying to integrate from 0 to infinity, so like within the range of integration, the only infinite discontinuity that occurs within this range is 0, okay? So this is the case where the infinite discontinuity occurs at the limits of integration. So we can write this as 0 plus infinity, so that we know that later we want to approach 0 from the positive side, okay? Okay, now we can try to evaluate this integral. Okay, so for this integral, actually, we have to do u substitution, okay? And the u substitution we're going to use is u equals square root of x. This may seem a little bit odd, but you can see that if u is equal to square root of x, then du should equal to 2 square root of x taken the reciprocal dx, okay? You're differentiating square root of x, which is x to the 1/2 power, okay? Okay, so remember that like here, we're doing a definite integral or like improper integral. So once you're using u substitution, you have to see where the limits of integration go, okay? So when x goes to infinity, then because u is square root of x, then u also goes to infinity. This is easy. And when x is going to 0 from the positive side, here you can see that here we have a 0 positive, which means that later we want to let x go to 0 from the positive side. Then when x goes to 0 from the positive side, then u also goes to 0 from the positive side, right? Because when x is going to 0, like a smaller and smaller positive number, you take the square root, then it is still a smaller and smaller positive number, okay? So you can see that this is equal to integration of 0 plus into infinity 1 over, now we have 1 over square root of x, right? Here, dx. But eventually we want 1 over 2 square root of x, so we have a 2 here and place a 2 here to balance it. And for the remainder, we have 1 over x plus 1. But we do not want any x left, right? Fortunately, we can write x plus 1 as root x squared plus 1. Okay? The reason why we write this is because we know that square root of x is u. So like later when we do u substitution, we can just substitute square root of x with u. Okay? Okay, now then we can proceed on with the u substitution, which is equal to 2. And for the limits of integration, when x goes to 0 plus, u goes to 0 plus. And when x goes to infinity, u also goes to infinity. Okay? Now, for the integral, we have u squared plus 1. And 1 over 2 square root x dx is just du. Okay? Okay, now we can see that we're integrating 1 over u squared plus 1, which you should know by heart that this should be arctangent. Okay, so this is equal to 2 times arctangent u. You want to evaluate it. Okay. Okay, so now there are 2 terms we want to evaluate, which both involves limits. Okay, here for the first term, for the upper limit, x is going to, sorry, it is not x, u is going to infinity. And this is for arctangent u. And for the second one, u is going to 0 from the positive side, and we want to add arctangent u. Okay. Okay. And previously, when we talked about like improper integrals, we have argued that this one should actually go to pi over 2. Okay, so this is pi over 2. And for arctangent u, actually arctangent u is continuous at x equals 0. So like taking the right limit, taking the left limit, or directly plugging 0 is actually the same. So you can just plug in 0. So arctangent 0 is 0 because tangent 0 is 0. So arctangent 0 is also 0. So you have 0 here, which is equal to pi. Okay? Okay, so you can see that this improper integral actually have 2 flavors. So like the first flavor is that it has an infinity at its limit of integration. And the second flavor is that at the limit of integration, it has the integrand has an infinite discontinuity. And the way you tackle it, like for the first part, you just take the limit to infinity when you're evaluating the antiderivatives. And for the second reason for improper integral, you write this 0 as 0 plus to remind you that later when you're trying to evaluate the value of the antiderivative, you must let your variable go to 0 from the positive side. Okay? Okay, now let's look at D. Okay. So in D, we want to evaluate negative 2 to 1 over x squared dx. Okay. Okay, at first glance, this does not look like an improper integral, but if you see the integrand, which is 1 over x squared, when x is equal to 0, it actually blows up, right? It blows up to infinity. So, or like if you try to graph 1 over x squared, you would lead to something like this, right? So as x goes to 0 from either side, it blows up to infinity. So for this type of integrand, where we're trying to integrate from negative 2 to 1, that is including where the infinite discontinuity occurs, then we have to split this integral into from negative 2 to 0, and then from 0 to 1. Okay? And we know that like at 0, it has a infinite discontinuity, so you can write this as 0 negative, and here as 0 positive, to remind you that after you find the antiderivative, you have to take the right limit or left limit, okay? Okay, so now we can proceed on with the antidifferentiation. So the antiderivative of 1 over x squared is something like 1 over x, right? But we're missing a negative sign, so here we have negative 1 over x, which is 1 antiderivative for 1 over x squared, okay? So now you have 0, negative 2, plus this one is also the same. So here we have 1, 0, positive, okay? So now we, for the upper limit for the first term, you have limit x goes to 0, negative 1 half, not 1 over x. Okay, now we're minus negative 1 over negative 2. Okay, this is the first term. And for the second term, we can just plug in 1. And then for the lower limit of integration, this is minus limit x goes to 0 plus. Okay. Okay. So you can see that here, this term is negative 1 half. Okay. This term is negative 1 half, and this term is 1, the negative 1, okay? So here we have, this is negative 2/3 plus limit x goes to 0, negative 1 over x, minus limit x goes to 0, positive negative 1, okay? Now let's evaluate these two. When x goes to 0 from the negative side, then 1 over x should go to negative infinity, right? Because x is a very small number, but it's negative. So 1 over x should be a very large number, which is negative. So negative 1 over x should go to infinity, okay? Because 1 over x goes to negative infinity. And when x goes to 0 plus, which is like x is approaching 0 from the right-hand side, then 1 over x should go to positive infinity. So negative 1 over x goes to negative infinity, okay? Okay, so you can see that for the second term, it goes to positive infinity. And for the third term, it goes to negative infinity because we have a negative sign here, negative sign here. So this becomes like a negative infinity plus infinity. So the negative 2/3 does not matter because this would go to infinity, okay? Okay, notice that here, if you ignored the infinite discontinuity, and then you just wrote that, and this is equal to negative 1 over x, 1, negative 2, then you would end up with negative 1 over 1 minus negative 1 over negative 2, okay? So this would be negative, so here I have a mistake here, this is 3 over 2, negative 3 over 2. So this is definitely wrong, right? Because you can see that from the graph, 1 over x squared is always positive, so why would you have an area under curve of a negative number? So this is not correct. It is because you're omitting the infinite discontinuity. So if you incorporate the infinite discontinuity, you would get the correct answer, which is infinity. That means that from negative 1, for example, here, negative 2 to 1, like basically both these area actually goes to infinity. So the integral here goes to infinity. Okay, now let's look at E. So for E here, we want to find the integral from 1 to 3 x over x squared minus 4 dx, okay? So first, before we do any anti-differentiation, we want to make sure that this is not this is an improper integral or not, okay? So x over x squared minus 4 actually have 2 points of infinite discontinuity. One is at x equals 2, one is at x equals -2, okay? For both these values, when you plug it into the integrand, it would become like a negative infinity or positive infinity because the denominator would go to 0. However, because we're now integrating from 1 to 3, then there is only one infinite discontinuity that is relevant, which is x equals 2. Okay, so because x equals 2 is a infinite discontinuity, then we should split this integral into two parts, which is one go from 1 to 2 and from 2 to 3. Okay, and to remind us that because these two integrals are still improper integrals, where 2 is the infinite discontinuity, we can write 2 negative here and 2 positive here. Okay, so later we can pick the right limit, like left limit or right limit. Okay, so now we can proceed on to find the antiderivatives. So for this integrand, it should be obvious that you can use u substitution. So if you use u equals x squared minus 4, then du is equal to 2x dx. Okay, and because we're doing definite integrals or improper integrals, we have to see where the limit integration goes after the u substitution. So when x goes to x equals to 1, then u is equal to 1 squared minus 4, so it's -3. When x is equal to 3, then u is 3 squared minus 4, which is 9 minus 4, which is 5. When x goes to 2 from the negative side, then x squared is going to 4 from the negative side, right? So u is going to 0 from the negative side. And when x is going to 2 from the positive side, and x squared is going to 4 from the positive side. So u is going to 0 from the positive side, okay? Okay, now we have our ingredients, so we can try to prep for u substitution. So here we want 2x dx, right? So we have a 1/2 here, so that 1 goes to negative x squared minus 4 2x dx. Okay, plus from 2 plus to 3, 1 over x squared minus 4 2x dx. Okay, now we can do u substitution. So we have 1/2. Here we have to substitute the limits of integration. So when x equals 1, u goes to -3. When x goes to 2 from the negative side, u goes to 0 from the negative side. And here for the integrand, we have 1 over u. And the differential, we have engineered it so that it is equal to du. Okay, for the second integral, the lower limit of integration, when x is going to 2 from the positive side, u is going to 0 from the positive side. And when x is equal to 3, u is equal to 5. And the rest is the same with the with the first integral, okay? Okay, now we can see that here for the first, here we can find the antiderivative of 1 over u, which is logarithm of the absolute value of u, right? So we have log u to -3 plus log u 0 positive 5. Okay, so this is equal to, here this is limit, u goes to 0 negative log u minus log the absolute value of -3 plus, so we should write something like this, okay? So plus log the absolute value of 5 minus the limit of u goes to 0 plus log u. Okay? Okay. So this is equal to limit u goes to, okay? This is the first term, and the second term I will use this term, okay? Okay, so here we have limit u goes to 0 from the positive side, log u, okay? And for the rest of the two terms, it is plus log 5 minus log 3. Okay? Okay, so this is 1/2 limit. When u goes to 0 from the negative side, and you have like an absolute value of u, and basically this is equal to u goes to 0 from the positive side, log u. Okay, because u is going to the 0 from the negative side, but here you have the absolute value of u. So this is like basically u is going to the 0 from the positive side, but you take out the absolute value, okay? And for the second one, you have limit u to the u goes to 0 from the positive side, and because u is going to 0 from the positive side, then absolute value of u is just u, okay? So this is log u. Okay? Okay, be cautious that like although these two things look the same, but you cannot cancel them out, okay? Because you have to make sure that they converge, or like they can evaluate to some number before you can say that, okay, I can cancel them out. If they are infinity, then this becomes infinity minus infinity, which is a indeterminate form, and then it just does not converge, okay? And actually that is the case because when u goes to 0 from the positive side, then log u is shooting down to negative infinity, right? We said that the graph for y equals log x or y equals log u, when u is 1 is 0, right? But when u goes to 0, it goes to negative infinity. So this one is negative infinity. This one is also going to negative infinity. So you have a something like negative infinity minus negative infinity. So this is a indeterminate form, and it does not converge, okay? Okay. And like alternatively, like if you omit it, like splitting this improper integral into two parts, then you would get like 1/2 like log 5 minus log 3, which is not correct, okay? The correct answer is that this improper integral does not converge, and then this one is just not correct, okay? Okay, lastly, let's look at f. Okay. For f, we have integral from 1 to 6 x squared cube root of x squared minus 9 dx. Okay, for this integral, first we see that, okay, we want to know if it is improper. And actually, it is improper when the denominator evaluates to 0, right? And this happens when x equals 3 or negative 3. And between these two, like x equals 3 is actually within our limits of integration, which is 1 to 6. So we have to split this integral into two parts, where it is 1 to 3, and then it's 3 to 6. Okay, to remind us of the direction of the limits, we can write 3 minus here and 3 plus here, okay? Okay. Now let's see, for the integrand, if we want to find the antiderivative, we can use u substitution, right? Because if u equals x squared minus 9, then du is equal to 2x dx, and like the x is the multiple of here, right? And because this is a improper integral or definite integral, now when we look at the limits of integration, when x is equal to 1, then u is equal to 1 squared minus 9, which is negative 8. When x is equal to 6, then u is equal to 36 minus 9, so it's 27. When x goes to 3 from the negative side, then x squared should go to 9 from the negative side. So u should go to 0 from the negative side, because u is x squared minus 9. When x goes to 3 from the positive side, then like u goes to 0 from the positive side, okay? So now, let's engineer our integrand and differential. So we need 2x dx, so we have 1/2 here. We have 2x dx. Sorry. Here we have 1. Okay. Okay, now we can do u substitution. So here we have from 1 to 3 minus, but now we have transformed it to u. So 1 corresponds to negative 8, and going to 3 from the negative side is going to 0 from the negative side. So this is 1 over the cube root of u, because u is x squared minus 9. And the differential here is du. Okay? So here this is 0 plus, and 6 corresponds to 27. Okay? So we can use the power rule to get the antiderivative, like one antiderivative of 1 over cube root of u, because 1 over cube root of u is just 1 over u to the 1/3, which is u to the negative 1/3. Okay, so you can use the power rule and get, this is u to the 2 over 3 and 3 over 2. Okay. Okay, now let's look at these numbers. So you can see that u to the 2 over 3 is actually continuous at 0. Okay, because it is continuous at 0, so then like the left limit, right limit, and the value at 0 are like both coincide. Okay, so we can just plug in 0 into it. So this is equal to 1/2 0 minus 0 minus 3 over 2 minus 8 2 over 3. Okay, and for the second term we have 3 over 2 27 to the 2 over 3 minus 0. Okay, and remember that like x to the 2 over 3 is just the cube root of x taken the square. So this is equal to 1/2 negative 3 over 2 negative 8, okay, plus 3 over 2 27 taken the cube root and then squared. Okay, and the cube root of 8, negative 8, the cube root of negative 8 is just negative 2. So this is negative 3 over 2 negative 2 squared plus 3 over 2, and the cube root of 27 is 3, so this is 3 squared. Okay, so this is equal to 1/2. This is 4, so this is negative. Sorry. This is equal to 1 over 2 times 3 over 2. I factor out the 3 over 2, okay? So within it is negative 2 times 9, okay? So eventually you get 15 over 4. Okay? So this is the result for this improper integral. So like from these examples, you can see that when you have a infinite discontinuity for your integrand within the range of integration, then you have to be very, very careful, because the improper integral may not converge or with these like infinite discontinuities within it. Like it can still converge, like for subproblem F, we still have a convergent result here. But sometimes, like depending on your integrand, it may not converge, so you have to be very careful. Okay? Okay, let's have a break here. Okay, now let's look at another application of integrals, which is related to statistics. Suppose that we're interested in a quantity with possible value ranging from a interval that is continuous. So for example, if we're interested in the height of all the students in the university, so the height can range from a wide range of value, right? And it is continuous because, like, for example, it can be 160, 160.5, 160.25. Then like these are all possible values for the height. So we say that this variable, or like this quantity we are interested, is continuous. So suppose x like is representing the height of the students in the university. Okay, so x is continuous because it can take on a lot of different numbers within the range. And also, x is a random variable, because if you take any two students, then like their height will not be the same, right? So like the height you observe would be random. So we call this type of x is a continuous random variable. Okay, so in contrast, there are discrete random variables. For example, if y is the outcome when you throw a die, okay, so now the outcome of y is not continuous anymore, because it can only take on 1, 2, 3, 4, 5, 6, and it's not taking a continuous range of values. Okay, so it is discrete. But y is still a random variable, because every time you throw out a die, it can be either 1, 2, 3, 4, or 5, 6. So it is random. So we call this a discrete random variable. Okay. Okay, there are a lot of examples on like continuous random variables. So for example, we talk about height, right? So we can also talk about weight, like the weight of students in the university. Or we can talk about time. For example, like if you have a queue and the customers are waiting to get served, then the length of time each customer is spending waiting in the queue can be still described as a continuous random variable. Okay, or like if you're interested in stocks, then the price of stock over time is also a continuous random variable, because it is random, it is fluctuating over time, and it is more or less continuous because it is taking like a lot of different values within an interval. Okay, so for any random variables, the most intuitive way to describe this random variable is to specify the probability of observing each value of this random variable. So this is more evident in discrete random variables. For example, if you're interested in the outcome of a die, then we can describe this discrete random variable by specifying what is the probability, which we write P, what is the probability of y equals 1 and probability of y equals 2, up to what is the probability of y equals 6. And we know that these probabilities are all 1 over 6 if the die is a fair dice. Okay, so using this description, you have described all the information contained within the discrete random variable, because you have known all the probabilities of all its outcomes. Okay, and suppose that you're not rolling a fair die. For example, the die is not fair that there is a 1/4 probability of it being 4 and a 1/4 probability of it being 5 and a 1/2 probability of it being 6. Okay, so now this is another die which is not fair, but you can still describe its outcome using a discrete random variable. And to describe this discrete random variable, you can just write out all the probabilities of its possible outcomes. Okay, this is for discrete random variables, which it is easy because you know there are finite possibilities of outcomes, and you can just list out the probabilities of these outcomes one by one. But for continuous random variables, it is not so easy because, for example, if you're interested in the height of a student in the university, then what is the probability of a student's height is exactly like 160 over 234. Like basically there's like virtually probability 0, okay? Because the possible outcome is continuous, so like basically every single point on this like a probable outcome it has probability 0. So for continuous random variables, we will provide a function called probability density function. So here, suppose we are interested in the x, okay? Let's say it's the height of students, okay, in a university, okay? So we will define a function called the probability density function, which is defined as probability of A is less than equal to x or less than equal to b is equal to integral a to b f of x dx, okay? So we have defined a new function here, and this fx of x is called the probability density function for x, okay? So if you plot this probability density function on a Cartesian plane, for example, here, like the height of students, maybe it should look something like this, and like the average should be something like 160. Okay, so this is x, and this is y equals fx. Okay, so this means that once you have this probability density function, and suppose I want to know the probability of a student's height between a and b, I can just compute the definite integral from a to b for this function. Okay, so in this case, you can see that it fits our intuition before that, like the probability of like the height being exactly one number is 0, because for example, if we want to know the probability of the height is exactly 160.234, then like you will have to write 160.234, 160.234, right? Because this means that the height is greater or equal to 160.234 and also less than or equal to 160.234, right? So this means the height is exactly this number. But if you plug this in to the definite integral, we know that because the upper limit and the lower limit is the same number, so this is equal to 0, okay? So this fits our claim that for continuous random variables, the probability of any single point that occurs is 0, but you can give a probability of the random variable taking on a range of values. For example, here is a to b, okay? So this is the definition of probability density functions, and based on this definition, we have we can deduce two requirements for a function to be a probability density function, okay? So first, because here you're integrating this probability density function to get probabilities, right? So its area under curve should never be less than 0, because we know that probabilities cannot be less than 0. Like at most it should be 0, right? So it is 0 or positive. So we know that fx of x is 0 or positive for all x, okay? So this is the first requirement for one function to be a probability density function, okay? And the second one is that because this is a continuous random variable, so like at most it can take on values from like negative infinity to positive infinity, right? You can think of like the for any quantity you're interested in, the outcome of it should still be on the like real line, right? Real number line. So we know that if you try to compute something like probability of negative infinity, like this is not very rigorous, but like you know what I mean, that the probability of x like being on this number line should be equal to 1, right? So based on our definition, this means that if you integrate the probability density function from negative infinity to positive infinity, then it should arrive at 1. So these are the two requirements for a function to be a probability density function, okay? So now let's look at an example. Let's look at example 7. Let's look at example 7.13. Okay, suppose that the random variable for the waiting time, which is measured in minutes, for a queue of customers is denoted as x, okay? And we provide the probability density for x, which is written as fx of x is equal to 1/2 e to the negative x over 2 when x is greater or equal to 0. And it is 0 when x is smaller than 0, okay? Okay, now we try to verify if this function is actually a legit probability density function, okay? We talked a little while before that like when a function is a probability density function, it should satisfy two requirements, right? These two requirements. So we first verify the first requirement, which is f of x, and like fx of x should be greater or equal to 0 for all x. And this is trivial because for x is less than 0, it is just 0, and 0 is greater or equal to 0, right? And for x greater or equal to 0, we can see that this is an exponential function, and we know that exponential functions are always greater than 0, okay? So a is trivial, okay? We have talked about this, like it is like a greater or equal to 0, okay? Okay, and for the second requirement, we have to do some calculation with improper integrals, right? We want to make sure that when fx of x is integrated from negative infinity to positive infinity, we want to make sure this is equal to 1, okay? So now let's try to evaluate this improper integral. So here, because fx of x is defined using a piecewise definition, right? So we can split up this integral into two parts. So here, one part is from negative infinity to 0, and the second part is from 0 to infinity. Okay? So within negative infinity to 0, we see that f of fx of x should be 0, right? Because the values within this integration, within this integration is like negative, like this is taking on negative negative values of x. So for the first term, we can write this as 0 dx. Okay? And for the second term, here x is taking on positive values, so we can write 1/2 e to the negative x over 2. Okay? Okay, now for the first term, if you integrate 0, you get like the antiderivative. One of the antiderivative is just a constant. So here a constant, and if you it's a constant, right? So if you plug in the upper limit and lower limit, would be constant minus constant. So the first definite integral here should be 0. okay? Or alternatively, you can think of like if you integrate y equals 0 and take its area under curve, then because like there's no area under curve, it is just the x-axis, so it has no area under curve, so this should be 0, okay? Okay, now let's look at the second integral, which is a improper integral we're trying to evaluate. So first, here we can take out 1/2 out of the integral. And then you can use u substitution, right? So you let u be the exponent, which is a negative x over 2. Then we know that du should be negative 1/2 dx, okay? You differentiate negative x over 2. And because this is a definite or like improper integral, you should know how the limits of integration changes when you do u substitution. So when x is equal to 0, we know that u is equal to 0, okay? U is negative x over 2. And when x goes to infinity, then u should go to negative infinity, okay? Because here u is negative x over 2. Okay, so now let's try to engineer our integrand and differential to get our desired u substitution, okay? So we have 0 minus 0. Okay, so here within the the differential, we need negative 1/2 dx. So we move the 1/2 back in and give a negative sign in the front so that we have negative 1/2 within the integral. Okay, so now we're prepped to do to do u substitution. Okay, so for u substitution, when we substitute into u, the infinity becomes negative infinity, right? And the 0 becomes 0. We have derived this here. Okay, and here you have e to the u, and the differential is the u. So because here you have negative infinity and 0, but you have a negative sign here, so you can swap the upper and lower limits of integral and eliminate the negative sign, so it is equal to something like this, right? Okay, so now we can find the antiderivative. The antiderivative of e to the u is just e to the u, okay? You want to evaluate it by 0 and negative infinity, okay? So for the upper limit, this would equal to 1, right? And for the limit, for a lower limit, you can see that we actually need limits to like evaluate e to u, evaluate it at negative infinity. But you can do it in your head, because when u goes to negative infinity, then it is a very negative and like a large magnitude number. So from the graph of e to the u, you know that when u goes to negative infinity, the value of e to the u should actually go to 0. So this is equal to 1 minus 0 is equal to 1. So we have verified that when you integrate fx of x over the real line, which is from negative infinity to positive infinity, you get 1, right? So this satisfied our second requirement for probability density function. So we have now verified that fx of x is actually a probability density function. Okay, now let's look at subproblem B. So we want to calculate the probability of a customer waiting between 1 to 2 minutes, okay? So in mathematical terms, we want to compute the probability of 1 is smaller or equal to x and smaller than equal to 2, right? This means that the waiting time is between 1 and 2 minutes. And by definition, this can be evaluated by integrating fx of x from 1 to 2, right? And because now x is taking on positive values, we can substitute fx of x with the definition here, okay? So it is 1/2 e to the negative x to the 2 dx, okay? So now the rest is just like evaluating the definite integral. So you pull out the 1/2 and then Actually, we're doing the same thing before. So u is equal to negative x over 2. So du is equal to negative 1/2 dx. And then we figure out the upper and lower limit of integration. So when x is equal to 2, u should be equal to negative 1. And when x is equal to 1, u should be equal to negative half. Right? Okay. So we can write this is equal to integration from 1 to 2, and then e to the negative x over 2. And for dx, we have to engineer it so that we have negative 1/2 dx for the u substitution, right? So you have a negative sign here. Okay. So now this is equal to negative and the integration. Then the lower limit of integration previously is 1, but after we do u substitution, it becomes negative 1/2. Okay. And here 2 becomes negative 1. Okay. And this is e to the u du. So this is equal to negative 1, negative 1/2. Here we're flipping the upper and lower limits of integral so that we can eliminate the negative sign in the front. So eventually you get e to the u evaluated at negative 1/2 and negative 1. Okay, so this is equal to e to the negative 1/2 minus e to the 1, negative 1. Okay, so this is our answer here. Okay, so now let's look at C. And for C, we're trying to find the probability of a customer waiting less than 1 minute. Okay, so based on this probability density function, we know that as x is less than 0, fx of x is 0. This implies that it is not possible for x to be negative, which matches our intuition, because you cannot wait like negative 1 minute, right? So when we're saying that the probability of a customer waiting less than 1 minute, actually we're implying that the customer is waiting between 0 minutes and 1 minute. So actually what we want is probability of 0 is less than or equal to x and less than or equal to 1, which can be evaluated using the same definition as this. Okay. Okay. So here, x is still taking on positive values, so you can substitute it with 1/2 times e to the x, negative x over 2, okay? Okay, now we use a different approach. Previously, we always used a u substitution, right? But here, you can directly, just using your head, you can know that 1/2 e to the negative x over 2, when you find its antiderivative, you would get negative e to the negative x over 2, okay? This is because, like, when you look at this integrand, you know that its antiderivative should be some multiple of like e to the negative x over 2, right? So you try to differentiate this e to the negative x over 2, and you will get negative 1/2 times e to the negative x over 2 using chain rule, right? So we know that like actually we want 1/2, not negative 1/2 as a constant before the exponential function. So we add a negative sign here, so the whole thing differentiates differentiates to our desired integrand. Okay. Okay. Both approaches work. Like the previous approach using u is like more rigorous, but like the second approach here is like faster. Okay. So you can evaluate this by writing this is equal to negative e to the negative e to the negative 1/2 minus negative e to the 0, right? So this is equal to e to the 0 minus e to the negative 1/2, which is 1 minus, sorry, this is not 1/2. Oh yeah, it's 1/2 too. So negative 1/2. Okay, So this is our final answer. Okay, so now we know that for a continuous random variable, if you're given the function, then you can evaluate any like the probability of this variable taking on any interval of value. And the way you do it is just to integrate its a probability density function within this interval. Okay. Okay, now we have the probability density function in hand. We can now calculate some of the most important characteristics for a random variable. Okay, so these two characteristics are expected value. Okay, expected value and variance. Okay. So in statistics, if you're told that like x is a random variable, the first thing we would think is that what is the expected value of x and what is the variance of x. So now let's look first at the expected value, okay? So for a random variable, its expected value is the average value you would see from this random variable. Okay, so for example, previously we talked about like x representing the waiting time for customers in the queue, right? So if you want to know the average time that the customer will be waiting, then you should look at the expected value of x. So x, then if you take the expected value, most of the time we will write something like this: expected value of x, or like e of x. Okay, and to know how to derive the expected value using probability density functions, first let's forget the like continuous random variables, and let's first look at discrete random variables, which we gave an example using a die, right? So for a die, which can be 1, 2, 3, 4, 5, 6 as its outcome. And further, we'll assume that this is a fair die. So like for any possible outcome, it has like equal probability. So because a die has 6 faces, right? So the probability of it taking on 1 or 2 or 3 to 6 is all 1/6, right? We talked about this before when we were talking about how to describe a variable, right? Here we say that the probability of it taking on any value should be 1/6. Okay, so if I ask you that like what is the average outcome you would expect when you throw out a die, then like intuitively you would say that if, like for example, I let the outcome of a die be y, then expectation of y, okay, this means that like average outcome of y should be 1 plus 2 plus 3 plus 4 plus 5 plus 6/6, right? You're just averaging all the outcomes because you know that it's a fair die, so that every outcome has like equal probability. You can just add them up and then divide by 6. This is equal to 3.5, right? So this is one way you can think of when we're trying to find the expected value of y. But you can also write this in another way, right? You can write this as 1 times 1/6 plus 2 times 1/6 plus 3 times 1/6 plus 4 times 1/6 plus 5 times 1/6, 1 plus 6 times 1/6. So the expression above and below is actually the same. They all evaluate to 3.5. But for this expression below, we know that here we're multiplying the outcome by its probability, right? Here, the outcome we chose is 1, and the probability of y being 1, meaning that you have a outcome of 1 for the die, is 1/6. And for another possible outcome value 2, it also have a probability of 1/6. So here you're adding all possible outcomes timed by their probability. Okay, so you're adding these up to get your expectation. Okay, so for example, we talked about another possibility that the die is not fair, right? So for example, if the die is not fair and we see it has probabilities like this, okay? 1/4, 1/4, and 1/2 for y equals 4, 5, and 6. Then, like for example, I write here, unfair die. Let's say like the outcome for this unfair die is z. Then the probability, the expected value for z, you would write it as 4 times 1/4, because we know that getting outcome of 4, you have a 1/4 probability. And also you have 1/4 probability of getting the outcome of 5, and eventually you get 1/2 probability of getting the outcome 6. So the expected value of z, where z is the outcome of this fair die, can be written as this, and this evaluates to 5.25, okay? Okay, so this is how you calculate the expected value for a discrete random variable. We say discrete because the outcome of a die can only take on 1, 2, 3, 4, 5, 6, which is not continuous. Okay, now we're trying to derive the formula for the expected value for a continuous variable, okay? And we say that we cannot get the probability of a continuous variable being equal to one specific value, because like for any specific value, like the probability of this continuous random variable being equal to that value is 0, right? We talked about this before. So we have to be clever and make use of our probability density function, okay? So suppose x is a continuous random variable. Okay, and we have with probability density function. Sorry. Okay, fx of x. So here we can like plot fx of x along x, right? This is fx of x. Okay, so it's something like this. Okay. Okay, so now we can slice the x-axis into very small chunks, like we did in like the calculation of areas or volumes. Okay, so suppose we slice it here. Okay, so this is x, and this is x plus dx. Okay, okay, so now we have an area under curve. Okay. Okay, so for this very small strip, which is between x and x plus dx, so now the area under curve here, which is fx of x times dx, right? We found this like when we were trying to evaluate the area under curve for any function. Okay, so the area of this like blue strip can be approximated by this expression. Okay, but we say that the area under curve for probability density functions actually represents probability, right? So actually this is the probability of x is less than or equal to x, or less than or equal to x plus x. Okay, notice that like the capital X means the random variable, and then here we are using small x to represent like this particular x coordinate. Okay, so we know that this the expression on the left is the probability of like this random variable x being between x and x plus delta x, x plus dx. Okay. Okay, and like to find the expectation value, we say that you have to multiply the possible outcome by its probability of for this outcome to appear, right? And for this very small strip, actually x can take on any value between x and x plus dx, but because if we let dx be small enough, then every value within this interval is very close to x, right? So we can multiply x by the probability, which is fx of x dx, and this constitute as like one of the terms. Like we can think of like it is one of the terms like in the discrete variables, right? So we want to add up all these terms to get our expectation value. And we say that in the integral world, if you want to add up like these very small very small quantities, you just add a integral sign before it. And because we want to add up all possible values of x, right? So here we want to integrate from negative infinity to positive infinity, okay? Okay, so this is actually the definition for the expected value of x when x is a continuous random variable, okay? You just integrate x times fx of x, which is its probability density function. You integrate this from negative infinity to positive infinity, and then you get the expectation, okay? Okay, aside from expected value, there is another characteristic of a random variable that is very important, which is variance, okay? So when we talk about variance, we're actually like trying to know like how dispersed is the outcomes of a random variable, okay? So for example, like if for random variable A, the probability distribution function is shaped like this. Like it can, like basically it can only take values like within a very small range, okay? This fa of A, x, okay? And suppose there is another variable which is B, which has a probability density function like this. Then like the possible values it can take is spanning at a larger interval, right? So we would say that the variance of B is greater than the variance of A, okay? And the way we define variance is like we want to know the expectation value of this, for example, x, of this random variable and its distance to its mean, okay? This means that I want to know that what is the average distance between the outcome of this random variable and its mean. So like it is centered, okay? So intuitively, if you want to define variance, you would do something like this, right? So like within the expectation, you're calculating the distance between the outcome of this random variable and its mean, okay? So this is intuitive, but like in math, we find that this expression is actually hard to maneuver because it does not have a very good mathematical property, right? Mathematical properties. So usually we do not use absolute values. Instead, we use squares, okay? So we want to calculate the average of the squared distance between the outcome and like the expected value, okay? So we know that like for example for B here, then the probable outcome relative to its mean can be very far, right? So for example, if EB is here, then there are a lot of possible values here that is very far from EB. So like the so this value minus expectation of B taken the square would be very large. So this expression would be very large, right? So in contrast, if here we're trying to evaluate the variance of A, and this is the expectation of A, okay? So you know that no matter how you draw possible outcomes from A, it is very close to expectation of A. So the distance between them and A taken the square is small. So you have a very small variance, okay? Okay, so to evaluate this expectation, actually you can follow the definition because the expectation can be written as negative infinity to positive infinity. This is the value, right? And you want to time it by the probability. Previously, when we tried to come up with the definition of expected value, we actually use this technique that we slice up the x-axis and then multiply the outcome of x by the small chunk of like probability. Here we're not looking at the expectation value of x, but the expectation value of x minus expectation of x squared. Okay, so we do the same thing for the second term. This is the probability, but for the first term we're not looking at x. The outcome, like the outcome we're interested here, is x minus expectation of x squared. Okay, so this is how you evaluate the variance, like using probability density functions. Notice that here we have an expectation of x here, but this, after you evaluate it, this is just a number. For example, like if the expectation of value of x is 3, then you should evaluate something like x minus 3 squared. Okay, so expected value of x is just a number, like within this improper integral. Okay, so this expression is like usable, but sometimes it is easier to transform it into another type of expression, right? So here you have x minus expectation of x taken the square, so we can expand it and get x squared minus 2 expectation of x plus expectation of x, the whole taken the square. Okay, now you can split up these three terms. Okay, so the first one would be integrating x squared times fx of x dx, and the second one would be negative 2. We take it out, and ex we also take it out. Okay, because we know that ex is just a number here. Sorry, here x should be a capital. Okay, so expectation of x is actually a number, so you can kick it out of the integral and get okay. So for the second term, you have a constant term of negative 2 expectation of x. This is just a constant multiple, so you pull it out of the integration sign, so you get this. And at last you can pull out expectation of x squared out of the integral and get this. Okay. Okay, so now we have 3 improper integrals, and let's look at how they can be expressed using expectation. So for the first one, you can see that you're multiplying x squared by this like small chunk of probability, right? So similarly, we can write this as the expectation of x squared. Okay, because you're multiplying the value of x squared by small chunks of probability. Okay, and for the second term, you have negative 2 expectation of x, and for this one, this is actually the definition for expectation of x, right? So this is expectation of x times expectation of x. And for the third term, you can see that because fx of x is a probability density function, if you integrate it from negative infinity to positive infinity, it should evaluate to 1. So this value goes to 1. So this, the last the last quantity would be expectation of x squared. Okay, so here you have 2 times expectation of x times expectation of x, so this is equal to expectation of x squared minus 2 times expectation of x taken the square plus expectation of x taken the square. Okay, so this is equal to expectation of x squared minus expectation of x taken the square. Okay, so this is an alternative formula you can use to evaluate the variance of x, which usually we will write variance of x. Okay. Okay, so now let's look at an example to see how we can evaluate the expected value and variance of a random variable. Okay, So in example 7.14, like we can write this. So we had a random variable x that is describing the waiting time for a queue of customers, right? And we say that this variable x has a probability density function shaped like this. Okay. Okay, so we want to know how long should the customer be expected to wait on average. Okay, so this is, we're trying to find the average waiting time. So because x is the waiting time, so the average waiting time should be the expectation of x, right? So we want to find the expectation of x. To find the expectation of x, we can follow the definition. You should integrate from negative infinity to positive infinity x times fx of x, which is the probability density function for x. Okay, so like before, we can split this integral into x times f of x from negative infinity to 0 and 0 to infinity. Okay, and for the first one, because fx of x is 0 when x is taking negative value, so the integrand is 0. So this whole integral goes to 0. Okay. And for the second integral, we can plug in the expression for the probability density function when x is greater or equal to 0, which is 1/2 times e to the x over 2 to the power. Okay. Okay, now you see that we have 1/2 integral x e to the x over 2 dx. Okay, so for this integral, we have to use integration by part. Okay, so for integration by part, we can let u equals x dv dx equals e to the negative x over 2, or we can let u equals e to the negative x over 2 and dv dx is equal to x. However, this choice is not wise, because here when you try to differentiate u, it becomes like negative 1/2 e to the negative x over 2, which is not simpler. And if you integrate this, you get 1/2 x squared, which is more complicated. Okay, so this is not getting you anywhere, so we discard this choice and use this choice. Okay, so under this choice, we have du dx should be equal to 1, and v is negative 2 e to the negative x over 2. You can verify this by differentiate this term, and you can get back to our original dv dx. Okay, so we can apply the formula for integration by parts. So the first term should be uv, right? So u v, remember that you have to evaluate it from 0 to infinity, and subtracted by another integral, which is integrating du times v. So du is 1, and v is negative 2 e to the x over 2 dx. Okay. Okay, so here you have, for the first term, this is negative x e to the negative x over 2. Okay, I'm multiplying the 1/2 into the parentheses. Okay, and for the second term, you have plus, because you have a negative sign here, negative sign here. Okay, so this is plus, and then you multiply the 1/2 into the integrand. So here the 2 actually cancels out, so you get e to the negative x over 2 dx. Okay, and previously we say that the antiderivative of e to the negative x over 2 is actually easy, because here we have already derived it. Okay, when dv dx is e to the negative x over 2, we say v is equal to negative 2 times e to the negative x over 2. So the antiderivative can be written as negative 2 e to the x over 2. Okay. Okay. Now we have to plug in the numbers into the antiderivatives, right? And because we have infinity as integration limits, actually we have to take the limit for this type of evaluation. Okay, so here you have x goes to negative infinity, negative x e to negative x over 2. Okay, minus, you plug in 0 into this expression, then you get 0. Okay, because this is x times e to the negative x over 2. So there's a 0 here, so you get 0. Okay? And for the second expression, when you plug in negative, here you have to plug in infinity. So, sorry. This. So x goes to infinity, negative 2 e to the x over 2. Okay, minus, here you want to plug in 0 into it. So this is negative 2 times e to the 0. And e to the 0 is 1. So this is negative 2. Okay? Okay, so now let's tackle these two limits. For the second limit, it is easier. Because when x goes to infinity, then x over 2 also goes to infinity. So negative x over 2 goes to negative infinity. So here, this exponent goes to negative infinity. And we have talked about this a lot of times. So if you raise e to a value that is going to negative infinity, it goes to 0, right? So this whole thing goes to 0. Okay? And for the first limit, it is actually more cumbersome because we will have to use L'Hopital's rule. Okay? So let's rewrite this as, this is negative x over e to the negative x over 2. Sorry, there's no negative here because we have put it in the denominator, so it is e to the x over 2. Okay, and here this term is 0 and this term is 0, and we're left with plus 2. Okay. And for this term, we see that when you use the plug-in method, that plug in infinity into x, you see that this goes to negative infinity, right? And this goes to infinity. So this is a indeterminate form under the form of infinity over infinity. So we can use L'Hopital's rule. So this is equal to negative x, you take the derivative, and e to the x over 2, you also take the derivative. Okay? So for the numerator, you're left with negative 1. For a denominator, you get e to the x over 2, and using chain rule, you have a 1/2 in the front. Okay? Now you can use the plug-in method again. So for the numerator, you get negative 1. For the denominator, when x goes to infinity, this term goes to infinity, right? So this goes to infinity. So you're dividing negative 1 by a very, very large positive number. So it will approach 0 from the negative side. So this is equal to 0 plus 2, which is equal to 2. Okay? So the expected value is 2. So the expected waiting time for each customer is 2 minutes. Okay? Okay, so now let's look at subproblem B. In subproblem B, we want to find the variance of the waiting time. That means that we want to find variance of x, okay? And for this term, we'll use our new formula that ease us in the evaluation of the variance, which is expectation of x squared minus expectation of x taken squared. Okay? And previously, like in subproblem A, we have known that the expectation value of x should be 2, right? So this is equal to expectation of x squared minus 2 squared, which is equal to expectation of x squared minus 4. Okay, so now let's try to evaluate this quantity. And we know that this quantity can be evaluated using a integral from negative infinity to positive infinity. Here you want to find the expectation value of x squared, so you have to time x squared by the small strip of probability. Okay, and by the same virtue you can write this from negative infinity to 0 and from 0 to infinity. Okay, and for values of x that is less than 0, then fx of x should be 0. So this term goes to 0, okay? And for this term, we can write this is equal to x squared 1/2 e to the negative x over 2 dx. Okay, so this is equal to 1/2 okay. And for this integral, you can use integration by parts, like you can write out a formula, but you have to do it 2 times. Okay, so in this case, let's try the DI method or tabular method. Okay, so for the DI method, you have an integrand of 2 things multiplied together, right? So you have to decide which part of the integrand you have to put it on D column so that you differentiate it, and which part of the integrand you put in the I column where you repeatedly integrate it. Okay, and by our previous choice, we know that like the polynomial should like go through the D column, because we want to differentiate x squared so that it becomes x, and later it becomes a constant and eventually 0. Okay, so in the D column we have x squared, and the I column we have either e to the negative x over 2. Okay, now let's use the DI method. So here we have plus minus. Okay, okay. Now let's do the differentiation and integration. So like the derivative of x squared is 2x, and the antiderivative of this chunk should be negative 2e to the negative. Okay. Okay. So up until now, if we try to stop here, we will have to evaluate the integral of this. Okay, so this is still not easy because we have x times e to the negative x over 2. Okay, so we do it again, and then here we get 2, and here we get 4e to the negative x over 2. Okay, and to evaluate this, we have to integrate this. Although we know how to integrate this, I feel that like we can do this procedure again to get a 0 integrand for our final integral. Okay, so here I do it again and get this goes to 0, and this goes to negative 8 e to the negative x over 2. Okay, so for the DI method, you eventually you want to multiply this and this and this, and you add up the product, and for the last term you have the integral of these multiplied together, right? And the product of these is actually 0, like for the integral. So integrating 0 gives you a constant, and for definite integrals the constant can just be discarded. Okay, so the final antiderivative for x squared e to the negative x over 2 can be just written as the sum of the products of the like descending diagonals. Okay, so this means that this is equal to, this is x squared negative 2e to negative x over 2. Okay, so this one is this. Okay, and then we add negative 2x times 4e to the negative x over 2. Okay, this is the second descending diagonal. Okay, for the third term, you have plus 2 times negative 8 e to the x over 2. Okay, and the whole thing should be evaluated from infinity to 0, okay? Okay, we can multiply the 1/2 into the bracket, and also we can do some simplification, okay? So here, you notice that there is a negative sign here, and a negative sign here. So we take the negative sign out, but pull the 1/2 in, okay? And also, you see that every term have e to the negative x over 2, so we factor it out. So the thing left for the first term is 1/2 times 2 times x squared, right? So 1/2 times 2 times x squared. And the thing left for the second term, we have taken the negative sign out, and we have taken this e to the negative 2x x over 2 out. So it would be 1/2 times 8x, right? 4 times 2x. And for the third term, we have this is taken out, this is taken out, so this is 1/2 times 16. Okay. Maybe we should write it as this. Okay. Okay, so eventually you get this is x squared plus 4x plus 8 e to the negative x over 2. Okay, so for the first term, so for this term, we want to evaluate it at infinity and 0, right? So at infinity, this is like x goes to infinity, negative x squared plus 4x plus 8 e to the negative x over 2, okay? And for the second term, you have negative when x is plugged in at 0, like x squared and 4x all vanishes, so you have 8 here. And for the exponent, you have e to the 0, so it's 1, okay? So you get something like this. So if you rearrange it, you get 8 minus x goes to infinity, x squared plus, sorry. You can write this as x squared plus 4x plus 8, and in the denominator you have e to the x over 2, okay? So here the negative sign is moved out of the limit, and like we rewrite e to the negative x over 2 as e to the x over 2, but put in the denominator. Okay, now like you may know that what we're trying to do when we plug in x into this fraction, the numerator goes to infinity, right? X squared plus 4x, it just goes to infinity. And for the denominator, it also goes to infinity because you're taking the exponent of a very large number. So we have to use L'Hopital, right? So we use L'Hopital. So we differentiate the numerator, and we get 2x plus 4. And if we differentiate the denominator, we have 1/2 e to the x over 2. Okay, now we can try plug-in method, but here the numerator and denominator also both go to infinity, so we can use the L'Hopital's rules again. So this is 8 minus limit x goes to infinity. Here the numerator becomes 2 after a second differentiation, and the denominator we have 1/4 times e to the x over 2, okay? So now when x goes to infinity, this is just going to 2, okay? But the denominator is going to infinity. So this limit is going to 0 from the positive side, okay? So this is equal to 8 because the limit evaluates to 0. Okay, don't forget that like this 8 is just the expectation of x squared, okay? So the variance of x is expectation of x squared minus 4, which is 8 minus 4 is 4. Okay? So this concludes our introduction to how integrals can be used in statistics, especially like in the evaluation of the probability, the expected value, and the variance of a random variable, continuous random variable. Okay, that's all the time we have.